Okay. No, sorry, I didn't see you. So yeah. So for this second talk, we have the pleasure of having Andrew Gordon Wilson from NYU, who will tell us about understanding loss values from practical Bayesian deep learning. So to you.
Thanks so much. I'm really excited to be here at this very interesting event. I'm going to talk a bit about how I got interested in loss landscapes initially, how exploring loss landscapes and understanding their properties better has really directly inspired a lot of practically effective methods in Bayesian deep learning, but some of these methods are also not exclusive to Bayesian deep learning. And then at the end of the talk, I'll return to some of the very recent work we've been doing to try to sort of push our understanding further of what the structure of these loss landscapes actually is like. I think this topic is actually one of the sort of theory adjacent topics in deep learning that is very practically relevant. I think that neural nets have a lot more in common with other model classes than most people give them credit for. So I don't think having more parameters than data points, but still being able to generalize is either mysterious or unique to deep learning. This is something we've seen with non-parametric modeling, for instance. We know that linear models even can experience double descent. Being able to fit random labels perfectly, but still generalize well, I think is also not distinctive to neural nets. We can do this with Gaussian processes, etc. And there have been several demonstrations that many of the properties that we often sort of treat as mysterious in deep learning are actually also properties of other models. And we can understand these properties often through a probabilistic perspective. However, I do think that the loss landscapes of neural nets, the objectives that we typically use to train these models are fairly distinctive. And by understanding the geometric properties of these loss surfaces better, we actually truly can gain some insights into why deep neural nets have been so practically successful as a model class. So I got interested in loss landscapes and Bayesian deep learning about the same time in listening to a talk by Jorge Nosadal on optimization. So he was visiting Cornell when I was there, and he was using this figure on this slide to explain why the implicit biases of SGD might lead us towards solutions which generalize better. And he was arguing that SGD would typically find flatter solutions than maybe full batch gradient descent or standard quasi-Newton methods. And because there's often a horizontal shift between the train loss surface here in black and the test loss surface here in red, the flat solutions will tend to be less affected by this shift than the sharp solutions. And I think people can debate about that argument, but I think there are a lot of solid reasons to believe that flat solutions should generalize better. I think even if target and train are drawn from the same distribution, we would expect to see a shift and a horizontal shift unless our parameters were completely determined by the training data, which seems pretty implausible. But also we can think of Bayesian arguments, for instance, like flat solutions will pay less of an Occam penalty, etc. So it seemed like good intuition. But if it's true, then it also seemed to be extraordinarily good motivation for Bayesian deep learning, because for this argument to hold, the different parameters in the flat region of the loss would have to give rise to different functions. Otherwise, the flatness doesn't mean anything. So there were some papers around 2017 saying, well, you can reparameterize your model and kind of give the appearance or flatness or sharpness, and it doesn't really matter. Well, you can't do that if the different solutions in the flat region are actually giving you different functions. And for these arguments to hold, and I think they do generally, that's going to happen. And if that's true, then we're going to benefit a lot by combining those different functions together rather than just arbitrarily betting everything on one of them. And so just as a review, when we're doing Bayesian inference and making predictions, our ultimate objective is to compute this integral in equation 1. So the first part of this integral is just our usual predictive distribution conditioned on our parameters. So we have our targets, y, some test input x star, and our parameters of the neural net, the weights, w. And the second is the posterior over the weights given the data. Now, this Bayesian model average, where we want to use every possible setting of our parameters weighted by their posterior probabilities, will be pretty similar to classical training when the posterior is very well defined by the data. So if the posterior looks sort of like a delta function around some maximum likelihood or regularized maximum likelihood setting of parameters, then Bayesian model averaging will give us essentially the same answer as just standard procedures. However, in deep learning especially, we know that the posterior doesn't look anything like a delta function. We have these big flat regions, and moreover, the different parameters in these flat regions of the loss surface actually give rise to very different representations, very different types of functions. And so I think this is really great inspiration to do Bayesian deep learning, and I think Bayesian methods have the potential to have a much greater impact when used in conjunction with neural nets than with virtually every other model class. The challenge is being able to approximate this integral effectively. Now, this is obviously a hard integral to approximate, partly because the posterior, which can be written as, or loss can often be written as our negative log posterior, has all of this interesting topological structure. But we can still certainly do a lot better than just classical training, where we're approximating this posterior as a point mass. Even if, say, we use a Gaussian when the posterior is highly non-Gaussian, that might be a better approximation than a point mass, and we'll see practical benefits to continually improving our approximations of the posterior. So kind of as a step towards thinking about how we can approximate our posteriors better in deep learning, I was interested in just understanding the fundamental structure of these loss landscapes initially. And we found, curiously, that you could retrain a neural net with different initializations using SGD or whatever your favorite optimization procedure might be. And then you would get your two different solutions. And it was possible to actually walk from one solution to another without increasing the loss at all along some subspace. So it's very difficult typically to walk in a straight line from one, say, SGD trained solution to another. But you can find very, very, very simple curves like a quadratic Bezier curve or even a polygonal chain with a single turn, which will take you from one solution to the other without increasing the loss at all along the way. And so this was unexpected, and I would say this is something that's very distinctive of neural net loss landscapes. This is not something that you would see typically with other model classes, even model classes that involve multiple local optima. In fact, this shows that what we're finding with SGD aren't even really local optima. There are directions along which the loss surface is extremely flat. And so here we have another representation. This top image here is kind of the conventional view that we have about the different solutions that we might find in the neural net loss objective if we were to just retrain with different initializations. So here we have what appear to be isolated local optima. In the bottom left, we have the same two optima as we have in the bottom part of the first figure, connected along a polygonal chain in a different subspace. So just to be clear, this is not just an illustration, this is a real experiment. So here we've used, I think, like a ResNet 164. So this has over 1 million parameters. The weights that we're visualizing here are greater than 1 million dimensional. We're visualizing them in a plane. We're sort of, the colors that we see in these figures correspond to an affine composition of 3 settings of weights that define the plane. So in the bottom left here, we're looking at a different slice through this really, really high dimensional loss landscape. And in the bottom right, we've got a different slice where we have a quadratic Bezier curve, which will take us from one solution to another. So even though in random directions, it might appear that these different solutions are isolated, there are directions along which they can be connected. And we can think about how to do that. So here, I've got an expression for a polygonal chain taking us from W1 hat to W2 hat, which are 2 SGD trained solutions. The parameter that we want to learn here is theta, so it lives in the same space as W. It's a high dimensional parameter. And here we have a quadratic Bezier curve, which will take us again from W1 hat to W2 hat as we vary t from 0 to 1. So the way that we can discover these curves is to minimize our loss function uniformly in expectation over the curve. So what this ends up looking like is a line integral normalized by arc length. And if we're doing classification, our loss that we're integrating over could be, say, cross entropy. And so this is actually something that's very easy to estimate. We can just take samples from a uniform distribution and then gradient steps with respect to theta, and we can very reliably find these curves. These curves exist for a very wide range of model classes and applications. So not just convnets on image classification, but say LSTMs in language modeling, fully connected neural nets on tabular data, etc. And we can always find a polygonal chain with a single turn between these two solutions. Straight line paths typically cannot be found. Okay, so here's just a few fun visualizations of these loss landscapes from different perspectives. These are just different slices through this really high dimensional objective that we are typically optimizing to learn our parameters. And we can see that even in these slices, they're very, very multimodal and kind of messy loss surfaces. Okay, so then the next question was, well, how can we use this insight to do something practically exciting? I sometimes feel like we don't fully understand something, or we don't even understand something at all unless we can use that supposed understanding to do something practically interesting. And so we were thinking, well, there are all these solutions that seem to have low loss, and we sort of checked what the corresponding functions were, and interestingly, they were different from each other. So it would be maybe not as exciting if all the solutions were very homogeneous, but in fact, they are quite diverse. And we might actually expect this, since we know that if we retrain a neural network twice with different initializations, we actually do find quite different functions that make different predictions on the test set, even though they have the same values of loss on the training set, and they could often be averaged to make better predictions on the test set. And so we were playing with things like cyclical learning rate schedules, high frequency sort of cycles to kind of move around this loss landscape. And we were getting very used to visualizing the loss surfaces as we did this. And we noticed something kind of funny. So initially, we were averaging the functions associated with the different parameters along these modified learning rate schedules. But in visualizing what these weights actually looked like in these slices through the objective that we were traversing, we found that they seemed to be almost symmetrically oriented around points of good generalization on the test loss surface. So this is not on the training loss, this is the test error. And so we thought, okay, well, maybe there's something simpler we could do than averaging the functions. And maybe it's already occurred to you in just looking at this figure, we could instead actually just directly average the parameters. And so the idea is we modify our learning rate schedule. So we either use a cyclical learning rate schedule and average the parameters at the minima of each cycle, or we decay to a relatively high constant learning rate schedule and then take an equal average of the different SGD iterates and then use that average solution as our weight vector to make predictions. And so this actually did seem to work really well. And so the question then is, well, why does this work well? What's going on here? And so we found, for example, when we trained normally up to about 50% of the budget, and then ran SGD as usual, we might actually find a solution of lower loss than we would if we were to do this averaging procedure. But once we looked at the test error, everything had shifted. So this is almost an empirical realization on this slide of the figure that I had on the first slide of that cartoon figure of the horizontal shift between the training and the test loss surface. So we see that once there's this shift between the two surfaces, this average solution, which we're calling the stochastic weight averaging solution, tends to actually provide better generalization. If we walk away from each solution in random directions, the SGD and the SWA solutions, what we find is that we have to walk much further to increase the test error by a certain amount from the SWA solution than we do from the SGD solution. So this means that in random directions, the SWA solution is a lot flatter than the SGD solution. So some of you may have heard of sharpness aware minimization as method SAM that's getting popular lately, that's also explicitly designed to find flat solutions. SWA actually came a few years earlier and is a lot faster to run. So it's the same cost as standard training. And it also very reliably improves your generalization over SGD or ATOM or whatever other procedure that you might want to use. In this figure here, what we've done is we've looked at the path connecting the SGD and SWA solutions. So here at 0, we basically have the SWA solution, and we can see that on the train loss in green, we actually have a higher value of loss than we do for the SGD solution. But we also see that the SGD solution is near the periphery of very sharp ascent. And on the test loss, the SWA solution is centered on a good region of generalization, and we see that the SGD solution is actually providing poorer generalization. So in other words, the SWA solution in this direction is also on a much flatter part of the loss surface, even though the value of the loss is a little bit higher. We can understand also the success of this procedure in relation to the ensembling that we were doing before. So if we take very, very small steps in parameter space, as we were doing with these high frequency cyclical learning rate schedules, we can do a linearization and show that averaging the functions is actually going to be an approximation to averaging the weights and using the function with those average weights. And in fact, when we empirically look at the differences in the types of predictions we make with the average weights versus the average functions, they're often very similar, but using the average of the weights leads us to be able to make much faster test time predictions. So if we're doing a regular kind of ensemble of, say, K models, then our test time inference will take K times as much computations, whereas here we take exactly the same computation as just standard training. And so we considered this procedure over a variety of architectures and data sets and found that we always saw a quite reliable improvement in predictive performance without requiring additional computational expense, and that this works also with, Atom and other optimization procedures as well. One nice thing about stochastic weight averaging is additionally that you can start with a pre-trained model. So let's say you have a big neural net that's been trained on ImageNet and you don't want to have to train it again from scratch. You can actually just start with your pre-trained model, ramp up the learning rate, run for about 10 epochs and just average the iterates over those epochs and then use that average solution. And you'll see most of the benefits that you would get from working with SWA. One other intuition for why this works is to understand what happens when we do increase the learning rate with, say, SGD. What typically is going on is we have this loss valley where we have a bunch of different parameters that are all kind of contiguous all together, which are giving us very low training loss solutions. And when we run, say, SGD with a normal schedule, what happens is we just converge to a point near the periphery of this set. Maybe we move inside a little bit because of gradient noise and because of some of the arguments that people have made in favor of the implicit biases of these stochastic optimization procedures, but we don't move inside very much. Whereas if we increase the learning rate, we're basically spinning around these loss values. And by taking an equal average of the iterates, and that's actually very important to emphasize, an equal average, not an exponentially moving average, as we typically see with Polyak averaging, we get to move to a point that's centered in this valley of low loss solutions. And there are a lot of good reasons to believe that those points ought to provide better generalization. And in practice, that's indeed what we see. We also did an experiment here where we ramped up the learning rate very high, such that we're traversing actually quite bad models in green. But we still are able to see the benefits of this averaging procedure, where at about epoch 145, we start averaging and we see that we find a solution that generalizes better than if we use a standard learning rate schedule after 300 epochs. And so one of the conceptual takeaways in this experiment is that averaging bad models or bad functions will typically lead us to a bad solution, but averaging bad parameters will not, or parameters that are associated with, say, high loss functions, will not necessarily lead us to a bad solution if those parameters are symmetrically oriented around good solutions. And so this is a way, in some instances, to actually dramatically speed up your training procedure as well. Okay, so now that we sort of have contrived an optimization procedure that can benefit from flatness, the next question is, can we use some information that we get from the SGD trajectory to actually do scalable approximate Bayesian inference? And so one very simple thing we can do is, in addition to taking basically the first moment of these SGD iterates, we can also compute a low rank plus diagonal approximation of the second moment. So the idea, just to be clear, is we start with a standard learning rate, and then we decay whenever we would otherwise to a relatively high constant learning rate. And then we form a Gaussian posterior approximation with a mean equal to an equal average of the different parameters that we're traversing at this high constant learning rate, and a covariance matrix equal to basically just this sort of outer product of the iterates that we've computed, plus a diagonal term. And so this gives us our Gaussian posterior approximation. It essentially costs the same as just standard training. We just run this for a standard kind of computational budget that we would normally expend if we were training one of these models. And then once we have that Gaussian posterior approximation, we can sample from it to compute our approximate Bayesian model average, just in this equation here. So this is called SWA Gaussian. SWAG, it's in a paper called A Simple Baseline for Bayesian Uncertainty in Deep Learning, and that's because this is really as simple as it gets. It doesn't cost more than standard training. It's very easy to use, and we found that it reliably improves performance, and I'll get to that in a moment. To further understand, why this might work, we can look at these loss landscape visualizations in the subspace of the principal components of the different SGD iterates that we're traversing. And in those subspaces, we actually see that we're doing a very good job of kind of characterizing at least like the local properties of the posterior that we might want to approximate. There's also some theory showing that if you run SGD with a constant learning rate schedule, you're going to be eventually sampling from some kind of Gaussian distribution centered at one of the local optima, but that theory makes a lot of assumptions that don't actually hold in deep learning. So I find that these visualizations are also informative. So across quite a wide variety of problems, including pretty large scale problems like ImageNet with pretty big models, we see that this SWAG procedure leads to models which are much more well calibrated, so their confidence is much more aligned with the actual probabilities associated with the corresponding class labels over not just standard SGD, which is shown in green here. So here we have SWAG in blue, SGD in green, which is very overconfident. But also compared to a lot of more expensive and more elaborate procedures. We can gain some further insights also by visualizing the predictive distributions for regression. So one of the main features of Bayesian approaches is they're able to capture what's called epistemic uncertainty. And so that's model uncertainty, uncertainty over not knowing which solution is correct given limited information. That's uncertainty that we get through modeling the weights with the probability distribution. And that type of uncertainty should grow as we move away from the data, for instance, because there are many different curves that will be, a greater variety of curves that will be consistent with our data points far away from the data than right at the data. And so we see that this SWAG procedure does have that property. As we move away from the data, our predictive distribution expands and it kind of contracts as we move close to the data. Interestingly, this is not something that we really saw when we were looking at variational approaches for inference in Bayesian deep learning. The predictive distributions were quite homogeneous relative to this SWAG procedure. And so in order to understand why this procedure was working well, one of the experiments that I presented was visualizing the loss landscapes in the subspace defined by the principal components of the SGD iterates. And this made us consider whether it might actually make sense to do inference directly in that subspace. So one of the challenges to computing that integral I had on the second slide is just the very high dimensionality of the parameter space. And so our contention in this next direction I'm about to present is that even though the weight space is very, very high dimensional, a lot of the interesting functional variability might be possible to capture in an extremely low dimensional subspace. And so the idea is basically just represent all of our weights as a linear projection of a low dimensional vector and plus some kind of offset like an SGD solution or an SWA solution, and then do inference in the space of that low dimensional vector. And so here we write all of our weights as W hat, which could be, say, the SWA solution plus P times Z, where Z is now the variables that we're doing inference over. And so there are many choices we can make for this projection matrix. We could use a random projection. One of the most effective procedures that we used was to form P using the principal components. So the way that we can do that is we basically have a matrix, and the columns of that matrix are the iterates minus the mean. And then we can just take a partial SVD of that matrix, and that will give us this projection matrix. And so the idea here is that weight space variability is kind of a proxy for function space variability. And when we did that, we actually found that we could get much better accuracy and calibration than standard training, even if we were projecting into a 5-dimensional subspace. So there was still, sufficient variability in a 5-dimensional subspace to see a lot of benefits in doing Bayesian inference. And once we had that 5-dimensional subspace, of course, we could use whatever inference procedure we wanted. We even used slice sampling, which normally wouldn't scale to more than about, say, 20 dimensions. We also considered the mode connecting subspace. So here on the right, we have this visualization of the loss surface in 2 dimensions. In purple, we have a different parameter setting. And on the left, we have the corresponding functions. So we can see here very clearly that there's actually a lot of functional variability associated with the parameters on these connecting curves. And that was the approach that actually worked best if we used a projection into these mode connecting subspaces. And so indeed, we saw that we could improve both predictive accuracy and predictive likelihood, et cetera. I think sometimes when people think about Bayesian methods, they focus entirely on uncertainty representation, and it's not necessarily recognized that you can actually also significantly improve the predictive accuracy by doing this model average. Okay, so maybe 10 years ago, we had this picture that the loss landscape had a bunch of different local optima, and they were all isolated. We couldn't sort of move from one to another. And then with this work on mode connectivity, I think the intuition changed such that maybe we have like these wormhole-like passages between different solutions that we might find with SGD or some other optimization procedure. I actually believe that the loss landscape looks a bit more like the figure on the right. In fact, these different connecting curves are part of just a big kind of loss valley that contains, infinitely many of these curves. And towards trying to understand that, we considered whether it might be possible to find low loss simplices rather than just curves that connect different solutions together. So in the figure on the left here, we have two SGD trained solutions, W0 and W1, and two different connecting curves through theta1 and theta2. And this actually forms a simplex of low loss solutions that we can see in the bottom panel here, where we have basically infinitely many connecting curves between theta1 and theta0. And so in order to discover these simplices, we just modify our loss function so that we're trying to minimize loss uniformly in expectation over the simplex. And we basically just sequentially add points, connecting points between arbitrarily many local optima or solutions that we found with SGD. We also introduce a term which tries to maximize the volume of these simplices that we're finding. And so this is, again, a very simple procedure. It generalizes the mode connectivity result. We call this simplicial pointwise random optimization. And you can think of this as kind of training a whole part of the loss surface, maybe, rather than training a single model. And in fact, you can ensemble the points within these simplexes and find much better sort of solutions than what you would get using standard alternatives like deep ensembles, where you just kind of retrain your model independently a bunch of times and ensemble the results. So kind of pound for pound, if you condition on the amount of computation you're willing to expend this, this simplex approach will give you much better performance than many of the alternatives. And it can sort of be viewed as approximate Bayesian inference, where our posterior is one of these kind of big multidimensional simplices that we're finding. We also found that we could improve accuracy quite a bit under covariate shifts. So if we corrupted our data quite a lot, this procedure was especially good relative to alternatives like deep ensembles, et cetera, and other approximate Bayesian inference procedures. Interestingly, we have a different work, though, called Dangers of Bayesian Model Averaging Under Covariate Shift, that argues that there are some features of Bayesian model averaging that are actually naively not very well aligned at all with OD generalization and covariate shift, and one has to be very careful actually about the priors that one uses in those settings if they want to actually see the benefits of doing a model average. All right, so that's everything from me. Thank you.
Thank you very much for this very nice talk. So other questions from members of the audience and the panelists? Okay. Yes, Arthur.
Yeah, I was wondering, so in this stochastic weight average, I was wondering what's the effect of the batch size in a sense, because I guess it's important the fact that you use stochastic gradient descent, right?
Mm-hmm. So I think it's worked well over a variety of batch sizes. It definitely is important that it's a stochastic sort of search. Yeah, I think like it has been effective in the range of batch sizes that people normally use, but you're right, it does rely on doing stochastic optimization. So I guess we haven't been able to find a batch size at which it sort of breaks down, but if we wanted to, I'm sure we could.
Okay. Yeah.
So Burfin?
Yeah, thanks for the very nice talk. So I was wondering about your intuition about flatness in general, because you've been showing this one-dimensional connectivity curves, but that just implies one flat direction in this huge dimensional space. So what is really a flat minimum in this case like?
That's a great question, and it connects to I guess the very last part of the talk. So when we were doing this, I was kind of wondering, well, could you actually take this connecting point in the middle and rotate it, and would the loss surface be flat, in that rotated direction? And so this was kind of the motivation for the simplex optimization. So the idea that we start with however many local optima or SGD trained solutions that we want, and then we kind of sequentially add as many connecting points as we want to form a simplex, and we try to minimize the value of the loss for randomly sampled points within that simplex. And so we wanted to explore, well, how high dimensional might these simplices actually be? I mean, it became kind of challenging to investigate past a certain dimension, but we could find simplexes that were, say, 20, 30 dimensional relatively easily. These contained quite a large volume of all very low loss solutions. And so these one-dimensional curves do live in a much higher dimensional space. And we've been able to partially characterize that space further. So I think it's more the case that you just have this huge loss valley in the landscape, and we're just finding curves within that valley. When people talk about things like sharp versus flat minima, especially when we're talking about maybe, you know, SGD versus full batch gradient descent trained in a standard way, I think quite often it's just how far we've moved inside those valleys, rather than, you know, finding a solution that is sort of isolated but sharp and another solution that's isolated but flat. I think actually these solutions are all kind of connected together, and some procedures get to move inside more than others.
Thank you very much. So there is a question from Riccardo Tenderini in the audience. So concerning the stochastic weight averaging approach, have you eventually investigated the effect of the number of epochs after which the averaging procedure is made on the train and test accuracy?
Yes. We did find that if you use the same number of epochs as regular training, you see performance benefits, but you can continue to improve your performance up to about 1.5 times the normal computational budget. So this is just a small subset of results. Now this is a very well explored method, and it's natively implemented in PyTorch and so on. So if you just install PyTorch, you can call SWA immediately. And there are a few startups and so on that have done comparisons and so on. Yeah, the short answer is that you can continue to improve up to about 1.5 computational budgets. We've also looked at this in the context of low precision optimization, with the intuition partly that flat regions should be much more robust to quantization. You don't need to represent the weights with high precision if the whole region is very low loss around those weights. Also with the intuition that if you average solutions which have, you know, been randomly sort of rounded up with those that have been rounded down, you should be able to filter through quantization noise. And so we found in that instance that being pretty aggressive with the learning rate and doing a lot of averaging can enable you to actually get as good performance as full precision SGD, going all the way down to 8 bits for representing all of the numbers in your neural network. And so sometimes actually you can benefit even more from doing this procedure if you're thinking about, for example, low precision computation.
Thank you very much. So if there are no questions, I can ask. Wolfram.
Thanks a lot for this really nice talk. I really liked it. I have a question, and it relates to, it's sort of a follow-up on what Berfin just said. And so yesterday we had talks of Berfin, of course, but also of Rahim. And this makes me pose the following question. So, of course, you do this with all this complex data, yeah? But if I imagine that this data is generated from a real network that corresponds to the structure, so we would be in a teacher-student setup, and then the analysis of Berfin shows that one can actually make predictions of how these subspaces are connected. So when you do your simplex stuff at the end, or you construct these piecewise stuff, so the idea would be that it's related to permutations of the teacher network vectors in presence of duplications that are there because we are in an over-parameterized network. And so now the question is, is there a way to look at this? Have you thought about looking at this, whether you can interpret these intermediate points that you have to go through as sort of some specific points that would correspond to these intuitions?
Yeah, so if I understand correctly, the idea is because there are degeneracies in the way the network is parameterized, we could find many different parameter settings which could give us equally good loss values. One thing we've noticed in these simplexes is that the different points we find end up making very different predictions on the test sets. So they don't seem to be a result of over-parameterization in that respect. So we haven't actually found points that are due to symmetries. In the appendix of the mode connecting paper, we talk about how you can construct these such paths by exploiting symmetries and so on. But empirically, we don't seem to be actually discovering these solutions that arise through degeneracies in the parameterization. It actually seems to be just different functions that we get corresponding to the different parameters.
Okay, thanks.
Thanks.
Thank you very much. Are there other questions? Can ask a question, perhaps. So for the stochastic weight averaging, is there a way to maybe do a kind of clever averaging, like you would do a second procedure where you would do an optimization maybe on a validation set or something, and try to find what are the better weights that you could take?
It's a great question. I mean, we wondered why an equal average was so effective. Of course, the idea of iterate averaging, dates back quite a while in optimization with things like Rupert's averaging, Polyak Rupert averaging, etc. I think even in deep learning, people had done things like exponentially moving averages with standard learning rate schedules. These sort of different variants of averaging didn't tend to actually make that much of a difference in generalization performance. It might smooth the trajectory of SGD a little bit, but it doesn't really sort of change your final answer that much. And things like Polyak averaging and convex optimization were mostly motivated for improved rates of convergence, not for finding solutions which generalize better. So we found that even though this is such a simple procedure, the details were extraordinarily important in order to sort of benefit from doing this. So doing an equal average seemed to be crucial, as well as modifying the learning rate schedule, either using a cyclical schedule or decaying to a quite high constant learning rate and then taking an equal average. We thought that there might be some other way to weight these points that could sort of lead us to better performance. Maybe we want to weight them by the value of loss or something in analogy with Bayesian model averaging. Maybe we could do some sort of validation procedure that could help us combine these better. But what we found is it was hard to improve performance very much to kind of warrant the additional complexity in what we would get as a result. And so it's actually been frustratingly difficult to improve on just simple equal averaging. We've managed to get maybe a little bit better sometimes, but this is often involving a much more complex procedure. Yeah, I think it would be very interesting to see if there are sort of other ways to combine these models effectively, or if we could sort of traverse over parameter spaces that aren't easily accessible to SGD. I mean, there's sort of this observation, for example, in Bayesian deep learning, that the simple procedure of just independently retraining your network a bunch of times and ensembling the results often leads to fairly good performance. And we can make this even more sort of Bayesian by trying to use, say, a mixture of Gaussians approximation, for instance, where rather than have a bunch of point masses representing the posterior, we have Gaussians, which are sort of integrating within those basins as well as across the different basins. And this does help, but it doesn't help like a lot. And so I think there's a question of sort of, well, how are we going to really substantially move beyond those types of procedures practically? And I think stochastic MCMC is one fairly exciting direction. So we've looked at stochastic MCMC, for instance, with cyclical learning rate schedules. We found that HMC, interestingly, Hamiltonian Monte Carlo, is actually able to naturally tunnel through these low energy barriers. And so even with a single chain of Hamiltonian Monte Carlo, you can do better than things like deep ensembles, but also better than what you would get with multiple chains, which was not something that I expected. I mean, HMC even has been known sometimes to struggle to explore multimodal loss landscapes, but this is not the case in deep learning. And we sort of have evidence that what's happening is it is able to actually find these very flat directions and exploit them, such that a single long chain of HMC is often better than multiple shorter chains. On the other hand, HMC is extraordinarily expensive and often impractical in deep learning, we were able to do these experiments because we partnered with Google and used hundreds of TPUs. But it's sort of an aspirational result in the sense that we know that HMC is actually doing something very different than all of the other approximate inference methods, including stochastic gradient Langevin dynamics, etc. And there's this open question of how we can explore the loss landscape as effectively at HMC, but you know, with a reasonable computational budget.
Sure, awesome, thanks. Okay, so just a small, you know, a very small-ish question. To be sure, the choice of nonlinearity doesn't really matter in all of the discussion, or does it?
Like whether it's like ReLU or sigmoidal or something. No, we found that we could get all the same results that I presented over a wide spectrum of activation functions.
Okay, thanks a lot. So yes, this you know, concludes the series of talks. Thanks to all the speakers for the wonderful talks and all the insights you've given us and all the people who participated. So now there is the